9 o'clock. All right. So welcome to my talk on metaprogramming. If you're out in the hall and can hear me, come in. No? Oh, anyways. So I have to apologize in advance for a little bit of bait and switch. When I originally wrote the submission for this talk, it was supposed to be kind of an application of metaclasses to work that I'm doing on networking. That was perhaps a bit ambitious because I didn't have a compiler that could actually solve the problems that I wanted to talk about. In fact, I still don't. So I ended up changing the order of my talks, so one of them was going to be specifically about the reflection aspects of metaprogramming and metaclasses, and this one is going to be pretty much about code generation. Unfortunately, this talk is not about really good examples of how you would use code generation in your problems. It is going to basically be a brain dump of things that I've done over the last month and a half, explaining how metaprogramming works. Or at least how generative programming works in C++, or at least how I've made it work in C++, which could be scary. Anyways, so my hope is that by kind of talking about the implementation details, or like the details of language semantics here, you guys can get a better idea of how you might be able to apply those particular features to problems that you guys have, even though I'm not going to be giving you the best examples of perhaps how to use these things, or even perhaps elegant syntax for how to express them. So, regular introduction. My name is Andrew Sutton. I'm a professor at the University of Akron. That's my university, not my offices. If you guys don't know where Akron is, it's in Northeast Ohio. This doesn't help you identify where it is on the map, but it is also the home of Goodyear. You guys are familiar with Goodyear from tires, I hope, and blimps. And that actually is Akron, and the university is in the bottom right-hand corner. You can tell because of the overspending on athletic fields. American University joke. Okay, so, that was not a button. What is the background of my talk here? Okay, so I actually started doing this work with Herb on metaclasses because he showed me this paper and I was really interested. And then I got kind of, what's the word I'm looking for? Self-motivated to work on it, because I figured out that I could take his ideas and actually apply them to an NSF-funded grant that I have to work on software-defined networking. And so this seemed like a good idea. Like, hey, take these metaclass ideas and apply them to building packet decoders and networking tools that you can use to write hopefully faster, hopefully safer, networking programs or libraries, essentially, right? And again, haven't quite gotten there yet, but we will at some point, hopefully. Okay, so the talk is basically, as I said, a follow-on from Wednesday's talk on reflection, or yesterday's talk on reflection. Yesterday I talked a lot about, specifically about how you take existing code and turn that into data that you can use to write algorithms. There was a little bit of code generation in there in the form of these like projection operators where you can use to turn, say, a reflection of a type back into a type specifier so that you could use it to declare a variable or a function or a parameter or a base class or whatever. This talk is actually just about how you create those values fresh, like without having an existing declaration, sort of. And then how do you turn around and actually emit those as real source code? So we're going from non-existent code to data to actual source code. So basically we're talking about programmable code generation. All right, let's see here. So when we started the metaclass work, we had a bunch of requirements on how you actually generate code, and they basically looked like this after we kind of worked through some of these ideas. We have to be able to write this thing called a metaprogram, or basically some kind of function or block of code that executes at compile time. So this is what I'm calling a metaprogram. We had to be able to read properties of classes, so enumerate the list of members of a class or member variables of a class. We had to be able to generate a new class to receive the output of whatever we're going to generate, and then kind of copy members from the original class into that output class, and maybe generate new members from that class, and insert those into the output class. And then also, finally, at the end of the day, generate the new class. Seems like it covers a lot of problems, right? No, because we missed a lot. So it turns out that actually really only covers two forms of code generation, which is that if you start with a class, you get a class. It turns out that a lot of the problems we ended up looking at require you to do way more than this, right? So generating a new class from an old class, that's great. We can do that. Generating non-member functions of a class, we didn't really support that so well. Sure, friend functions, great. But that's not really necessarily what you want to do with these things. You may actually also want to generate specializations in another namespace, for example, standard hash, which we all love to specialize. Yay, hashing tools and standard library. And then like the hardest thing we can actually figure out how to do is to take an existing function, for example, and wrap that with another function that somehow figures out what the parameters to the original function are, represents those as new parameters, adds parameters, modifies return type, and then wraps the call while performing analysis on the original arguments, and then analyzing the result type on the way back out. Not easy, and also not being discussed in this talk today. For very good reasons, like maybe it doesn't quite work yet. We also actually have this requirement that we really want to be able to precisely control where code is emitted. It may be that the code that you generate is not where you think it should be, but actually somewhere else. Maybe. And we kind of do this with templates, by the way, right? Like we have explicit instantiation to specifically say, put the specialization of this template instantiation right here in this particular translation unit. So we probably want to be able to do the same thing with code generation. Okay, so since, let's say Toronto, so early July, we've kind of been working on very specific use cases for these things and kind of ran against the wall with the original Metaclass proposal and started running into problems that we couldn't quite figure out how to do. So over the last month and a half, since late August or mid-August, basically, I've taken what we were doing in the Metaclass proposal and just said, okay, I'm going to put this over here on the side and start breaking down each of these use cases and trying to reduce it to the smallest possible fine-grained operations that we can possibly have. So just a real deconstruction of the entire problem set, and then start building it back up and providing tools that we can use to solve each one of these particular instances, right? The goal was really to, one of the main goals of this was to not try to get lost in the syntax of how you express these things. It turns out that doesn't really matter when you're trying to understand a problem. Like making elegant syntax is a second priority when you don't really know what you're doing. We need to start with the semantics first. Understand what these things actually are and what they do, and then we can go back and craft better syntax. So the syntax I'm showing for this is intentionally bad. I hope you like underscores. Anyways, so we also wanted to make sure that our injection mechanisms were building directly on top of reflection. We really didn't want to end up with kind of two different systems where you have this kind of reflection system over here and this kind of meta-programming system over here. They should be unified. And actually, they should actually layer on top of each other. You have reflection on the bottom, you should have meta-programming on top. And if you don't have a seamless approach to doing both of these things, then your language design is probably a little bit funky and it's going to require people to work a lot harder to do the things they want to do. So, first things first, we have to be able to write a metaprogram. We want to be able to write code that executes at compile time, kind of as you write it. So we actually ended up creating this const per block, which I'm actually calling a metaprogram or subprogram, meta subprogram. This is basically borrowed from David van de Voord's metacode proposal. He actually suggested using the word const per here. I think in his original proposals it was metacode or something like that. Same concept, or roughly the same concept. But inside these const per blocks, you can basically write any code that would normally execute in a const per function. And in fact, there is really no magic to doing this at all. If you write this, it is exactly equivalent to creating a const void function whose definition is just the contents of the block. And that second line is really just kind of a little bit of hackery that says evaluate it. And yes, that is a comma operator with a const void first operand and a zero. Yeah, it's weird, but it works. Compiler doesn't really do this, but that is effectively what you want to get out of these things. So there's really no magic behind any of this stuff. There's some magic behind some of it, but at least in this case, we're trying to build on existing language features and really not create something entirely new. That tends to be difficult. So the reason that we actually want to have these metaprograms is so that we can generate code. And this is basically a version of a slide that I cribbed from Herb's talk, although I rewrote it a little bit. So this is my toString function for enumeration. So you pass in an enumeration type and a particular value of that. And the goal is that you want to print out its name. And so I was going to laser point at this, but it's way over there. So effectively, the body of this is that you switch on the value, and the statement underneath the switch is actually a const per block, which turns out to actually be a declaration statement in this case, so it seems to be valid. And inside that block, you iterate over all of the enumerators in the class, which syntax we talked about yesterday. enumerators in the enum, sorry. And then we have this weird little arrow thing, which is labeled injection, hopefully in italics there. So the idea is that that would take the code inside of these braces and then emit that as a statement where it appears in the program, right? So ideally, like what we really have is basically this little meta program that gets replaced by a sequence of case statements as they come out of this. And hopefully the compiler is smart enough to actually stitch those together so you get a valid declaration. Hopefully. I make no promises that this works. But that is the effective idea of this. So the real question is what does that injection statement actually mean? What are we actually putting there? What are we doing? Well, you have to figure out what's inside of those things first. Are they tokens? Is it a string? It's not a string. It would have quotes if it were a string. Is it actually a fragment of source code? Which means, when I say a fragment of source code, I mean, is it a parsed and analyzed fragment of code, like an actual abstract syntax tree if you were building a parser? So, not an obvious answer, right? What do you guys think it is? What do you guys want it to be? Tokens? I heard tokens first. I'm kidding, I didn't hear tokens first. But tokens first, which is what I thought too, because I think that's what David's original proposal was. This is just a sequence of tokens. And actually my first implementation of this was exactly that. This is just a sequence of tokens enclosed in matching braces. Fantastic. When you go to generate these things, you actually have to kind of go back out and parse them and turn them back into legitimate code. And that actually worked. And it really only took me like 4 hours to get working in Clang. So a testament to the Clang compiler that I could do that quickly. Fantastic. Then I tried to do something interesting with them. Well, in fact, you might say that I tried to write just this slide. You see that E in there? Appears twice. That refers to a local variable in the context for block. It turns out that by the time you start reparsing this as a string of tokens, that E is no longer in scope. It has no meaning. It's just, oops, it is an unknown identifier. So I thought about this for a long time, and I'm like, okay, I can fix this. I can make this work. We'll just have this kind of escape mechanism that lets me push meaning into this stream of tokens, and then I'm like, oh, wait, I'm recreating the preprocessor but using C++ code. This might not be the right approach. We already have a preprocessor. We don't need a second one. Scratch that idea. So I threw that out, and then I immediately threw out strings too, because that's basically the same problem, except now you actually have to tokenize these at the same time. And I didn't really want to get into string interpolation, compile time string interpolation. It's a mess. So that leaves fragments of source code, which leads to its own very, very interesting problems. If you haven't thought about this, you might want to avoid it. It will make your head explode. It can make your head explode. Forward. Okay, so what are we actually going to inject? Declarations, sure. Statements, yes. Expressions, maybe not yet, for the same reason that we don't reflect on expressions. This would effectively give us a really interesting system that's basically equivalent to template Haskell, which is kind of neat. So ultimately, the goal is that we actually have to be able to build like fragments of source code that we're going to inject. We have to represent that as data. And then we need to define a bunch of operators that can take that data, the values of those particular things, and generate source code from them, and then put them somewhere in the program. Right? So this is where the details start getting fun. So this is a source code literal. And you can tell by the way this is bad syntax because of the underscores. So a source code literal introduces a fragment of code. And the way that I actually ended up spelling that was underscore underscore fragment to say this thing that follows is a fragment of code. It's not a real class. It's not a real statement. It's not a real enum. It is something that will potentially become a class or enum or statement or something later on, right? So it's followed by, a fragment is followed by some kind of a declaration or definition. So here C is a class fragment. And this doesn't say that we're going to try to inject the class C later somewhere on. We're going to inject the members of C somewhere later on. So fragments are not themselves injected, but the members of a fragment are. So this one injects an integer x, member variable x, into some class somewhere else, and a member function that returns x plus this arrow y. You will notice that y is not declared anywhere in this scope. It's an interesting problem. So effectively what we ended up doing was making this thing kind of like a template. So it's actually a dependent context. So when you actually do a lookup on this arrow y, you get back a pending lookup for a member later on. So we end up kind of getting another kind of two-stage instantiation. So frag ends up actually, the value of frag here, the thing that we actually get the value for, turns out being a reflection value. Like kind of the same thing that exactly the same thing that we were talking about later. Wednesday. which is essentially an empty class whose type is a specialization of something like class type. It's not quite that, it's a little bit more involved, but we'll see what it actually is in a second. So again, we can have fragments that define, we have class fragments, namespace fragments, so we'd have members that we want to inject into some kind of namespace or global scope, which is a nice thing to have. And then right now we also have block fragments, which basically contain statements that you can inject into a function somewhere, which you saw earlier on with the arrow example from Herb's talk on Wednesday. The rules for injecting fragments are pretty straightforward. You can really only inject a fragment into a like context. So you can inject class members into a class, you can inject namespace members into a namespace, you can inject enum members into an enum, or enumerators into an enum. We might be able to tweak the rules a little bit sometimes. Like if you have a namespace fragment, you might be able to inject that into a class by making all the members static. I don't know if that's useful. Somebody else can tell me if it is. We can support it if we need to. Okay, so class fragments look like this, again, so you have class node. You can use the name of the class fragment to refer to itself, so this is basically going to build an injection, a thing that you can inject to get sort of hooks for doubly linked list, I presume. You don't necessarily need a class name there, you can leave it out, it doesn't matter if you don't refer to the class, you just have an anonymous class fragment, it's fine. But if you need to refer to this or the type of this, then you can do so. Namespace fragments, basically what you think they are, except that the name is currently not optional due to a bug in the implementation. If you leave it off, you get like an anonymous namespace and then things get kind of weird. Clang does different things with those. But you know, namespace members and regular free member functions, they look like normal member functions. But you could use this, for example, to generate operator equals for some type if you have some well-defined simple function to call. You can declare a block fragment, which is basically what you saw earlier being injected. So a block fragment doesn't have a keyword, it's just a compound statement. In this case, we have a case statement with a return statement. So this would get injected somewhere, hopefully somewhere inside of a switch statement. And this is, by the way, there was an early implementation of this in, oh no, I left the link to my compiler off. I'll type it up there later, it'll be fine. So this, there was an early implementation of this and it worked actually quite nicely, and then I have deprioritized it, so it's kind of fallen by the way. So you can't quite do this yet anymore. Okay, so one of the things that actually ends up making these difficult is the fact that you actually want to push data into those fragments. So for example, if I want to declare a class fragment that declares a new variable, ID expert is a special function that creates an identifier. So that I'd have var underscore num, where num is resolved to, as this loop expands, each value of num through the loop. So var 0, var 1, var 2, something like that. In this case, we say that the fragment captures that value. Has anybody used template Haskell by any chance? Anybody looked at it? So they have a very similar operation called splicing. You can actually splice values into essentially a quoted string. That is very similar to what we're doing here. It's a good thing I read about that yesterday morning. Now I have a reference, frame of reference. Right? This turns out to be really interesting because that expression there is not actually evaluated in the way that you think it is. Like you could not, for example, write ++ num in this case. Oh, oops, I have a bug in my program. That should say ++ num at the bottom. You can't move that ++ n in or num into the expression, into the statement. Can't do it. It's captured by value, sort of. Right? So when you look at these things, there's actually three different things that happen here. There's sort of three phases to translating these things. So first you actually have to parse the fragment. We actually have to get a semantic representation of these things, an abstract syntax tree. Part of that means we actually have to determine the type of that source code literal, like what kind of value we're going to define by that thing. And then at some point in the future, when we evaluate these things, we have to compute the actual value of those things, which are pretty interesting also. And then during injection, of course, we actually have to substitute whatever that value is. We have to substitute information back into that value, the source code fragment value, to generate new source code. And that process is going to be a little bit like template instantiation, but a little bit different because you can't, for example, instantiate a namespace or an enum or whatever. So, actually, I guess you can instantiate an enum. Never mind, scratch that. If it's a member of a class template, you can do so. So the way that we actually do this is that we build these things out by kind of wrapping every fragment with this enclosing thing. And I'm using the word thing very vaguely here on purpose. It's not really a class, but you guys all know what a class is, so I wrote it as a class. Every local variable that appears in the scope where a fragment is used gets captured as a member of that fragment thing, the enclosing fragment. And it's really just a dependent name whose value is opaque, or magic in this case. So those are called placeholders. So now when we actually go to parse the body of the fragment, we have names like num or n or whatever that refer to these local things. And instead of actually referring outside of the scope of the fragment, they actually just refer back to these placeholders. And they are entirely dependent, which means they carry no type or value, which actually ends up having a nice property that it delays analysis. Right? And again, source code fragments are essentially templates. Without template parameters, they have placeholders. And by the way, the reason these aren't actually templates is because those things have non-type value. So if we tried to do this with template, we would be limited to substituting through types or substituting through integers. Or template names, but who does that stuff anyways? Okay, so the type of this thing is actually computed on the fly. Every time you have a source code fragment, you generate a type based on the reflection of the thing that it is. So this is the actual class generated that defines the type of that expression, the source code literal expression. It is a fragment class. Fragment underscore k is just a placeholder name. Call it whatever you want. But meta::class type is the reflection, the information about the fragment that you actually got, that you actually created. And then there are a couple of members. We actually create a member variable for every captured value whose type is the same. I don't really know what the type of x is, but it was an auto and iterating over a list of member variables. So it's probably something like field. I just forgot what it was, so I wrote decl type. And then n is the captured integer value there, and they're both constant because you don't want to modify these things. That would be pathological. And there's a constructor that takes those arguments in, and you can actually that does member-wise initialization. It's actually fairly straightforward. So the value of this thing, oh, sorry, I was going to walk through this here. Again, derives from the metaclass, so we have information about the type. I just said that. Again, capture member variables, skip that. So the value of this thing is actually just constructed by calling the constructor of that expression. So whenever you see something like fragment source code literal, or underscore fragment, all of that stuff is pulled together into an object of this one particular type, and that entire thing basically gets replaced by this single expression that just constructs a PR value of that particular type as it goes. So every source code literal is simply a const expr value of this type. That's all there is. Seems easy, right? Any questions so far? This is the obvious thing to do, of course. So the interesting thing is that because you've done it this way, frag now actually contains, that's variable frag actually contains all of the information that you need to get the original class fragment, all of its members, any information that happens to be in there, through reflection, of course, and it has all the values that you've captured associated with those things. You are binding all of this stuff together into a single value whose type can actually be unpacked into the original class fragment, unpacked from the original class fragment. This is a nice thing to do. Okay, the rest of this talk is what you do with those values. And again, excellent syntax with lots of underscores. It turns out there are really three things that we might want to do with these things. Or at least these are the three things that I've been able to identify from the use cases that we looked at. We want to be able to generate code. And I say when I say generate code, I mean we're going to take these values and we're going to put them somewhere. And I do mean somewhere. We don't really have control. When we generate code, we don't really have control over where it goes with this particular operation. You could inject code, which means that you take one of these reflection values and you inject it right here at its point in the program. Or we can extend an existing declaration by taking a value and injecting it in some other context, some other scope, some other declaration, possibly. This extend, by the way, is not actually implemented. So all of these things differ. The semantics of these things are generally the same, like the behaviors that you use to generate source code and put them into the compiler or into your program are basically the same operation. The biggest difference is where you actually put them, which I'm calling the injection site, because it seemed clever. So injection site basically can be a namespace class or function at this point. Again, we don't really have expression fragments or expression literals, so I don't know what to do with those yet. So all of these operators have kind of two forms. We have an injection operator that takes a reflection, which is basically an expression that computes a value. So we had like auto frag equals whatever. You could use frag as the expression after these things. Or if you don't really want to make a variable for it, you could just write the fragment directly after the operator name. It's just shorthand for declaring the variable and then injecting the variable. Same thing. So there is a little bit of syntactic nicety here. Okay, so generation. The idea behind generation or source code generation, this particular operation, is that we want to be able to kind of run a metaprogram and have that metaprogram be replaced by whatever code that we've actually generated. And this is why, by the way, why I say that, I'm not sure if it's on this slide yet here. Yeah. This is why it's somewhere, right? The generation operator, which isn't even on this slide, has no control over where the code is generated. Where that's generated is determined entirely by the context of where it's, of the program that executes it. Right? So this actually gives you the ability to take a metaprogram or a set of rules that generate code and decompose them into functions that you can actually call or reuse or isolate the logic of code generation in a way that is not a 2,000-line function that tries to generate an entire program. Those things are crazy. We should not do that. So for example, this one, ostensibly you would run this metaprogram inside of a class or after a class to generate definitions of equality and less based on some pre-existing operation in your class, like .equal or .less. And those things, those functions, we might actually just define like this. They're just regular const expr functions. This is great. So metaprogramming does not need to be this big new thing. We just have these interesting new facilities. So here we actually have the generate operator, which I forgot to bold and make red. So this generates a namespace fragment. So this is the second form of the syntax we're using. Namespace fragment just creates a bool operator equal with whatever t is, and returns and would expand to that thing. And again, this is why I say it's inject somewhere. That generate operator has no control over where the code is actually injected. It is determined entirely by the context in which it's executed. Useful, very useful. So the obvious, if you start with this, the result, because I didn't define the other function, would just be this code. Like the context, the metaprogram goes away, and all we have left are the programs, or the operators. And so the way this actually ends up working is that these things, this is terrible, these generate operators are actually a kind of side effect of metaprogram or const expr evaluation. I'm actually going to say metaprogram evaluation because you really don't want to start generating effects from every constant expression evaluation. Like you shouldn't be evaluating array bounds and get code generation side effects. That seems a little bit odd. So that only really happens when you execute a metaprogram. But you end up getting a queue of these things, and they're just generated, they're injected into your program at the point of execution in the order that you generate them. It's sort of a side effect. It's very monadic, I guess. Okay. Source code injection is kind of there's a nice relationship between source code injection and code generation. So you might, for example, inject something like this, or write something like this. So that would say evaluate whatever that function is, that expression. And as long as it returns a fragment, or a reflection, an object of meta : something, it will declare whatever that thing is right there in that program. That's what injection is. So the idea with this is that we can actually use this to start building up classes or namespaces by bringing things into scope. So you might think of generation as pushing things into a particular scope or pushing things out of your function to a side effect. These things actually, it lets you bring things into the scope that you're constructing. And again, right here means like declare this here. So for example, going back to our little class fragment here. So I actually really like this example because I'm actually returning a source code literal from a constant expression or const expr function. And again, not magic. We don't need special kinds of functions to do this stuff. It is just a const expr function. It returns a value whose type is determined by whatever magic I showed you before. And this thing just gives you a part of a class that you can put into something else that gives you next and previous links for example, a doubly linked list. Kind of a weird sort of intrusive doubly linked list, perhaps. Right? And so when you actually inject this thing, you write before struct my list inject make links, and you actually get hopefully what you would have expected to see. Note, you can kind of see how this might work by the class name C there being replaced by the name of the class in which it's injected. That's part of that template instantiation thing. There's some substitutions that happen as you do this. So injection and generation are actually pretty closely related. Yeah, right, sorry. So they're pretty closely related. So the inject thing was basically equivalent to having a meta program that evaluates the function and injects those members as a side effect. That happens to be, I think that's a nice property that they are that closely related. But other than that, I have no thoughts on that topic. Extension is actually really interesting because it lets you take a fragment of source code that you have in one place and inject it into something else. So for example, here's a use of extend that takes myList, which is a reflection, as an argument, and it would take whatever members of the fragment you have and inject them directly into the myList class. And if you're looking at that and going, hey, can I use this to do extension methods? The answer is probably yes. You can. That is just an application of the same rules that we're applying in slightly different ways. But again, this is the inject over their rule, right? Like, you can take this fragment and you can inject it into somebody else's code. Maybe. There are probably going to be some fairly strong rules. Assuming that this actually makes it anywhere out of this talk, there will probably be some fairly stringent restrictions on how you would actually do this. Like, don't inject things into standard containers. That might be frowned upon. Don't inject a member variable into an existing class. That would change the size and you would ruin somebody's function calls. Don't inject virtual functions. These are terrible, terrible things that you can do after a class has been defined. So those are probably going to be off limits. But injecting a normal function that just calls other member functions is not a particularly concerning thing. And that is especially true if you have modules where those extensions are isolated in scope, where you couldn't actually see those or affect the way that somebody else uses those programs. Okay, so you might write something like this. Here's my list. I can extend it with sort, and of course, it would just put that there. I should add, by the way, I don't know if this is implementable in every compiler. I can do it in Clang. I haven't done it, but I can do it. It's fairly straightforward. This is just one of those things that kind of fell out of the analysis and ended up getting sketched out. There was one other thing that I wanted to say about this. What did I want to say about this? Why am I asking you? I'll probably think about it later or remember it later. Anyways, so extension is a little bit odd. It's kind of the odd man out in these features. It's not really like injection or generation. There's no equivalent. There's no rule that you can say these things are kind of inverses of each other. I don't necessarily know that it adds really useful features except for method extension. Namespaces can already be reopened, so this really doesn't add functionality there. I don't know. But oh, right, now I remember what I was going to say. It does actually solve one particular problem that you have with metaprogramming, which is that you might want to create, for example, a class fragment in one function, return it, and add new members as you go. So you actually end up building up a class fragment through injection or through extension. And then finally, in a last stage, you can actually just emit the entire class or the fragment wherever you want it. Okay. So all of this is based on the ability to actually inject fragments. Well, that's not actually true. It's really based on the ability to inject a reflection. And you can reflect declarations, which means that you can actually inject existing declarations, which actually turned out to be one of the main requirements of the Metaclasses work. We had to be able to copy declarations from an original class into a resulting class. And so this actually works pretty straightforward, in a pretty straightforward way. If I want to, for example, take this class, so I have a class S that has 3 ints, and I have another class T. So I could, for example, inject S directly. That would give me a new nested class called S. So I'd have T, and then inside there class S. When you inject, by the way, a declaration, you don't inject its members, an existing declaration. You don't inject the members. It's not a fragment. It's an actual declaration. So you inject it in its entirety. Or you could open up you have a little meta program that kind of opens it up and walks through its list of members, and you can actually generate each member in turn. So the meta program in this example is going to generate int A, int B, int C, or however your compiler would hopefully represent that. Let's see here. So because you can inject existing declarations, you can also kind of make local modifications to them before you inject them. You can't do this with fragments yet. I'm not sure how useful it is. Mostly because a fragment is a container or declarations are not containers. For example, if you have a reference to a reflection of a member function, you may want to be able to make it virtual, so you can actually just set or call x.makeVirtual. This does not actually make that member function virtual. That would be crazy. This just sets a little local bit inside of that object that says, when you emit this code, make it virtual. From henceforth, when you generate this code, it shall be virtual. That's all it does. Oh, and I left in a version of expand. Expand should be spelled generate. If you guys see any other expands, replace that mentally with generate. I was tinkering with names before I gave the talk, last week actually. Okay, so like I said, injection is kind of like template instantiation. It's a little bit more involved, maybe a little bit less involved. No, it's more involved. So we have to deal with references to the fragment name. We have to substitute the name of the fragment for the name of the context into which it's being injected. All of those little placeholders that we captured, as we substitute through this to generate the new code, we actually have to replace references to those expressions with their values that we captured in the original constructor call, or the construction of that particular object. And then we actually have a couple of other little extra quirks that we have to kind of stitch up in order to make this stuff work. And all of those little quirks, by the way, kind of point to the fact that maybe we're trying to do things a little bit too implicitly, and we actually need a set of extra declarations to say, we expect these names to exist in particular contexts. Not sure yet. So for example, the model that you might want to think about is that if you're injecting, say, one definition, like a member function definition from one class into an output class, if that member function definition refers to its member variables, you can lift that out and then go drop it into this other class, and those references to member variables need to be restitched to hopefully members in the output class. So that's like an example of these little quirks that you have to deal with when you do this. Okay, so formally, semi-formally, quasi-formally. An injection is a reflection of a fragment to be applied. That's the value, the payload of these injection things. And remember, the type of that thing, the type of that value encodes a reference to the fragment that we have. So we can actually unpack that and get the AST node internally from those particular things. The value has all of the captured values as you evaluate those things. The injectee is the context that's actually receiving that. So the context in which the fragment was going to be injected. So the injection process actually instantiates all the members of the fragment, or if we're just talking about a single declaration, copying a declaration out, it basically just instantiates that thing, performing all those substitutions that we just talked about, and whatever little stitch-ups that we ended up needing. So here's my painstaking walkthrough of how this actually works. So I think I actually had this earlier, or something like it. So we have a struct S, two member variables, int n, bool b, and another class, cleverly named blah, that has a metaprogram that will, for each member variable of S, generate a new member variable in blah whose name will be var underscore some integer. That's the goal. So first thing that happens okay, so this is where things start getting a little weird. So remember, C++ works left to right, top to bottom. So as you walk through this thing, the first thing that you actually have to do as you process the context per block is you find that for loop, and the first thing that happens is that you actually decide that you need to expand it. So that unrolls the loop like this. So now we actually have two fragments that we're going to generate. So the first one is going to be get of the first member variable, and then we generate type name, x.type, id expr, whatever, right? So we actually just end up doing this twice. And we're going to look at the first one for the most part. So as we translate, so we basically unrolled this, which is one instantiation. That actually uses template instantiation to do that. So now we actually go through and analyze the results of that to create types. So if we look at just the first one, we have to assign a type to that generate, at least the fragment in the generate thing. So fragment 1 here refers to the type of the fragment or source code literal starting with class. And that's actually going to look like pretty much like what you saw before. So metaclass type x1, that x1 is an encoded reflection value. It's the pointer to the AST node. That's how you actually have a reference to that thing. The captured variable x is a reference to a field, because each version of x is actually a member variable, and the field is the name of the class that we use to reflect those things. And then we have the captured value n, which will hold what the value of n actually is at the time that you evaluate the fragment. So there's a couple different things that go on here. We have an expansion to unroll the loop. You generate the type of this thing, which allocates space for these objects. And none of this is evaluation yet. We still have to, at some point in the future, actually evaluate all this stuff to construct the value and then apply the injection. Okay. So at the time that you evaluate this, which is, by the way, when you get to the bottom of the context per block, right? Remember, the metaprogram is just a context per function. It gets called at the line below. So that's when you go back through and you start evaluating the program. So let's see, where were we? So as you do that, you create a value of the fragment, which the base class is going to be metaclass type x1. It's just basically just a default constructed class. It turns out to be empty. Well, it turns out to be empty with no modifications. The captured value of x, again, this is just an expression constructed by an empty object of type field. The only important thing there is the fact that it holds a pointer to the abstract syntax tree. And then captured in the first unrolling of this thing is going to be 0. Remember, if you get to the bottom of the loop, you increment that, and so, I left off the increment in my for loop. I put the for loop and the increment in the wrong place. Oh well, pretend that I did this correctly. Suspend disbelief. I realize I'm asking a lot, because this is pretty suspension-y. Okay, so n ends up being 0, and you can, if I had programmed this correctly, then in the second expansion of this, the value of n would be 1. And so that's the object that we're then going to inject. So now we can actually generate the code. So we're basically going to form this injection, right? Which is essentially just the value of the fragment that we're going to inject. And then we apply these substitutions. We replace the name of the fragment with the enclosing context, or the injectee. We replace every placeholder, as you substitute through this, you replace every placeholder in the original expression with a constant expression whose value is captured here. So that's why you can't modify the value in flight as you define these things. I couldn't write, for example, ++n in the ID expr. So it actually gets replaced by a constant expression of appropriate, I'm hitting the wrong button, of appropriate type. And then we find names that refer to local names of the enclosing scope and kind of replace those as needed to stitch them up. And then you end up with, well, let's see here. So one more slide. So as you evaluate these, and when you generate, so you actually generate the code. This is what actually ends up getting queued to be generated. You have type name meta field x2.type, which will give you bool in the first case and int in the second. ID expr var of 0 is the identifier. And so after you strip out all the sugar from those substitutions or projections, you end up with int var 0. And so eventually, after all of that, we've created a stupid class that has 2 member variables named var0 and var1. It's amazing, right? Yay. Okay, so a lot of work to get a little bit done, but it does scale up, or should scale up in interesting ways. Okay, so after all of that, we have these little low-level tools for building, for reflection and source code generation. How do you actually get back to metaclasses? Remember, metaclasses are this other thing. Well, original proposal was $class equals, or $class interface. And if we think about this, we can actually just define these in terms of things that we have with a little bit of help, right? So maybe interface is just a const expr function that takes some template parameter. In particular, that template parameter is probably the thing that you are declaring to be an interface. And if we want to actually make it kind of a little bit nicer syntax, we can just sort of invent syntax and nominate interface as a class key, which means you could use interface to introduce a struct in this case. Or if you want to make it a class, you could use it a class. So when you actually write these things, you might write interface ishape. And that interface there would mean go find something named interface that's been nominated as a class key, or if you find a name that's been nominated as a class key, start parsing it as if it were a struct or class or enum or whatever. And what it really means is maybe there's no magic at all. Just take the original class that you defined to be your interface, stuff it into a namespace, and then just call the meta function on that thing. Just call interface with the original specification of the class and generate the code that you need to generate. It doesn't necessarily lock you into generating a single class, right? Because you can generate non-local members, you could generate specializations in other namespaces. You have almost carte blanche to generate whatever you want from this single invocation. Right? So we can kind of by decomposing all this stuff, get back to a point where we can rebuild the original specification in terms of operations that actually kind of compose in an elegant way. Hopefully compose in an elegant way. I mean, except for all of the underscores, right? Okay, so metaprogramming needs a bottom-up approach. It really needs a bottom-up approach if you don't, if this is your first pass trying to implement it. You have to implement reflection first. It is important. You need that to do anything else. Having this idea of source code literals, like the actual implementation of this, or the idea of it, the model of these things, was turned out to be a really good idea. Because we now have a sort of uniform system of dealing with both reflection and values for code generation. Thinking about this in terms of primitive injection operations was also incredibly helpful. We can actually talk about what you need to do, what operations you need to generate code, and supply semantics that actually do the right thing. And then after all of that, we can start thinking about maybe abstraction mechanisms for these things, or sort of compositions of them that let you do particular things. And I will say that there is one thing that metaclasses give you that you cannot actually do with just these primitive tools, which is that I have interface iShape. That is not the class that you want, right? With only the primitive tools, I would have to generate a class with a slightly different name, like iShape_interface. This actually gives you a class replacement mechanism on top of what we've already defined. So we are actually replacing the original specification of iShape with the code that we're generating, or whatever code we actually end up generating from these things. And presumably, by the way, interface would generate a class named iShape. But that is just not shown. Okay, so that's a lot. That's a lot of work for a month and a half in Clang, especially when that's your development environment. Yes, my laptop and my dining room table are my office at times. But I still haven't actually talked about all the things that we actually need to do. And in particular, I haven't talked about what it means to wrap a function call, which turned out to be a nightmare of interesting semantics. In fact, one of the things that actually came out of that work is the fact that we might actually end up getting generalized pack expansion for tuples and classes and whatever, so that if you have a tuple, you can apply ... to it and generate a sequence of expressions. That may actually fall out of the work on generating parameters, or injecting parameters for the purpose of wrapping functions. Different talk, though. All right, so really quickly, acknowledgements, material based on, let's see, funded by an NSF grant and by Microsoft. Special thanks to Jennifer Yao, who I believe I saw over there somewhere, who's volunteering here today. She did a bunch of work on the original metaclass definitions last year. Thanks, Matt, for hosting a compiler. Are you slinking down in your chair? And again, thanks to anybody that was actually trying to use this thing, and I apologize for the bugs, but please quit sending bug reports. I'm not ignoring you, I'm just trying to move forward and not be perfect on this stuff. Let's see here. Questions? I'm sure there are no questions because this is perfectly understandable and obvious. Yes?
I feel that the whole thing can be simplified if you give the reflection objects full value semantics. Currently, you obtain the reflection object like out of thin air inside all the functions and all the translation functions, and make modifications in place. But it seems that if some of the translation functions can take reflection objects through the parameters by value and return them by value, things can be simplified.
Maybe. I like calling functions and getting values out of functions. I think that's a fairly simple model. I realize there's a lot of complexity here. I don't think that this gets much simpler.
Well,
I mean, we can talk about design alternatives offline, but so we probably should. I would like to hear good ideas for simplification because it is fairly complicated. But more questions. Who is first? All right.
Hi. Kind of interesting question. So now with all those mechanisms for injecting or using metaclasses, so only compiler knows what class will look like at the end before being actually compiled, right? So
I can't quite hear you.
Yeah.
Thank you.
So how do we generate documentation now? Do we inject comments as well, like doxygen and all that stuff, or compilers should start to generate documentation?
No, you can't inject comments. So the translation stages for this follow from like normal C++ rules. So whatever the normal translation rules are for C++, like comments get replaced by spaces. They disappear. The only thing that you have is the data or the abstract syntax trees from constructing those fragments at compile time.
Yeah, but like tools like doxygen, they probably won't be that smart to process injections.
There is an entirely separate question of tooling, right? Like this basically allows you to write a program that writes your programs.
Yeah.
And so tooling will need to catch up, or we'll need to start thinking about tooling very carefully. Debugging these things I do not expect to be particularly easy. And so we'll need to do some work to figure out how that happens. I have some thoughts on it, they're very premature, but you might actually be able to tie that back in through code generation.
Okay.
Sorry, documents type stuff.
Thanks.
Basically, you just need to keep track of where the original fragment was, and then, so every declaration that you write out has a link to the original fragment where it was, and then if you know the source code location of that, you can pull up the comments that are on top of it.
But do you have like a feeling that documentation should become part of, I don't know, standard?
Oh, so should documentation become part of the standard? No, documentation should not become part of the standard. That's the easy answer. Not part of the standard, maybe part of the style guideline. Sure.
Hi, I've got two questions actually. The first one is kind of bike-shaped one. So in C++, there's already a bunch of keywords that mean completely different thing in different contexts.
Yes.
Like static, for instance. So why did you choose constexpr for metaclasses?
For metaclasses, actually David van der Voort suggested it. I have a feeling that constexpr might start showing up in more and more places, unfortunately.
But
although hopefully we can get rid of the keyword in most cases. David suggested it. I liked it. It actually describes pretty accurately what that thing actually is and what it does. It is a constexpr block of code. It executes, ostensibly it executes as you translate it.
But isn't, I don't know, synthesize or generate a better option for this kind of thing?
Well, the program itself doesn't actually generate code. It's the generate operator or inject operator that actually performs that particular action. You can write a metaprogram that doesn't do anything. This is not a big deal. I mean, it's not particularly useful, but you can certainly write a program that just it counts from 1 to 10, and because it's constant expression, you have no side effects. But it's just a block of code that executes at compile time. So we wanted to keep. I think it's important to keep keep semantics separate.
Okay. And the second one is, with current version of the language, you can shoot yourself in the leg. And it seems like with this thing, you can blow off the entire lower body.
Yeah, sure.
How are you going to enforce some good practices on users?
Well, okay, so as a professor, I will not teach this until year 5 out of a 4-year degree.
Okay.
I expect that organizations will have their own strong policies about how this should be used, how this could be used. And almost certainly the first one will be don't use it. I think that'll be pretty popular, or pretty popular option.
Why would you need it then if everybody will forbid its usage?
Some people don't like adopting new features. So there's some interesting things that happen with this. We now have lots of compile time programming. So in large translation units, compile times may drop significantly. So people may, as a policy, opt to generate code externally rather than have the program generate its own code. I suspect that many places will initially say don't do this until the benefits start becoming very, very obvious.
Okay,
I think it'll be an evolution. It'll be a good story for that, I'm sure.
Okay, what's your bet on the version of standard that we are going to see this thing in? C++ 20, C++?
No, not C++ 20. Certainly not C++ 20. We might see like some of the early static reflection stuff in C++ 20. This is maybe C++ 23, but I'd be willing to bet more likely a TS first, and then further down the line.
Thank you.
Mm-hmm.
Fragments of classes and namespaces, if I understand this right, they will be typically injected in headers, and therefore they will be shared between multiple translation units. But in some situations, and specifically when we have dynamic libraries, we want them to go to a specific translation unit only. So what are your thoughts on having some control over this?
So yeah, I mean, I'm not particularly concerned with it. I mean, we're going to have we're going to write meta programs that generate code, and sometimes those will be in header files, and sometimes they won't. I look forward to the day where we can talk about this in terms of modules, where this starts becoming a little bit more sane. But I mean, ultimately, what you're doing is just replacing these compile time evaluations with the code that it actually generates, right? We already do this with templates. We already do it with macros. We already do it with, well, actually, that's about it. And so, like, that is a fact of life that we live with. So this is another way to Another slightly different way to generate code, hopefully in a slightly more intelligent manner, because we have access to the full source code as data. But it'll show up in header files. I don't think it'll have any impact I don't think it'll have significant impact on the code that actually relies on that, though, other than perhaps compile times.
Apart from compile times, I'm concerned about things like duplicating functions between multiple dynamic libraries, or even those functions having different meaning if they actually access some global variables also.
Oh, yeah, so this is, you can't duplicate functions. I mean, you can in different translation units, but then you get linker errors, right? But there's a rule that when you actually, like an unimplemented feature, that when you actually inject code, you have to do a redeclaration check, right? So I can't have a member, like a function called, or a member variable called int, or int n, and then generate a new int n. Like that's a duplicate definition. That gets rejected at the point you generate those things. It has to be. That said, the compiler doesn't do that yet, which means you get some interesting effects. But so we can't logically generate duplicate definitions or redefinitions in the same scope. You can certainly generate equivalent declarations in different translation units, but again, you can still do that today just by writing it by hand, and then you get translation error or linker errors, right? Yes.
Hello. How does reflection and injection interact with class templates?
All of this stuff lives below templates. So you cannot ask for information about, well, the semantics of all of these operations live below templates. So when you instantiate a template, that's when all this stuff gets applied. It doesn't happen beforehand. So if you don't, for example, execute metaprograms within a class template until you instantiate it. It applies to specialization, not the template.
So I can't, for example, inject something into an uninstantiated template?
I hope not, no.
Too bad, sorry.
Well, actually, maybe. I don't know yet. Yes?
Hey, not a question, but a comment.
Okay.
Coming from a common Lisp background, I'm used to macros being just implementable with normal functions, which I've always found particularly elegant and actually easy to understand. Mm-hmm. And so conversely, every other metaprogramming mechanism I've ever seen has been very difficult to understand and inelegant. So I'm very happy that you're doing that.
Oh,
thanks.
Thank you. Not a question, but thank you. All right, one more question.
So speaking about Lisp macros,
Yes.
So there's this notion of hygiene in Lisp macros.
Right.
So do we have the same issues here?
I hope not. So we need to make sure that we have rules that don't allow, okay. So you can't build a partially incomplete statement or thing. Like you can't build part of a class. You can build complete declarations. We have an issue where names can sometimes refer to things in like non-local scope where they might end up being sort of dangling references when you inject them. So we need to be careful to make sure that all the lookup rules are sane. But once we actually lock down the lookup rules for injection, or at least the rebinding rules for injection, then you're really just trafficking in kind of complete cohesive units of code, not parts of like a statement, for example.
So yeah, to weigh in on that as well, because I was trying to answer that same question while looking at your slides. I think, yes, we do have to worry about hygiene here the same way you do with Lisp macros. I also personally think it's not that big of a deal.
Okay.
You know, particularly because you have metaprogramming there's actually an easy way to say like, hey, I want these symbols to be unique things so that they are guaranteed not to clash with anything that you might otherwise have. Right. And that's kind of, yeah, that is the big weakness of Lisp macros, but like compared to what you get with every other system, I think it's a small price to pay.
Okay, thank you. Any other questions? All right, thanks for coming. Oh, no, one more question. The guy with the Metaclass shirt.
Yeah, so let's say I have a class template like pair, mm-hmm. and I don't like the names of first and second, but I would like them to be, I don't know, name and street or something like that. Could the user of my class provide these names? Like, could an ID expression, for instance, be a template parameter or something like that?
An ID expression can certainly be a template parameter. So the rule for ID expression, that operator, is just that it forms an unqualified ID. So anywhere an unqualified ID can appear. Actually, template parameters are just identifiers. They don't incorporate that parse. Technically not yet, but it's a thing to consider.
Okay.
Could you,
that would be crucial for my use cases.
Yeah. But could you potentially inject alternative names for first and second? No, probably not, because you'd have to modify, like that's part of you're essentially injecting name binding rules into a class. You certainly don't want to replace in pair the names first and second, because that would change potentially the structure of the class in a really weird way.
Not the current pair, of course, but if there were a named pair or something like that.
Maybe. I don't think I see a way to do that directly yet, but I will think about it.
Okay.
Any other questions? All right, well, thank you for coming.